Okay, so let's get started. Um, in the first few sessions, I'm going to cover a little bit about um, errors and how they compound when we do numerical uh, calculations, and uh, also how we represent or try to represent real numbers in a machine and some related issues. Okay, so that's the first couple of lectures or so in this course. Okay, um, so this first we're going to define a few things related to the notion of error. Okay, so the first, let's admit something. Uh, Everything that I do is wrong when it comes to numerical computation. And the what we hope to do is to be a little less wrong. And if we think a little bit about error, it helps us to be a little less wrong when we're doing numerical work. Okay, so and error is not something that we can avoid. If you're doing scientific computation for the purposes of physics, for example, you may be doing some measurements. Each measurement has an error. You're going to put those into those uh, numbers which have some error on them into a floating point operation, which then has its own associated errors. And then those results are fed into other floating point operations, which also have some errors. So there's no way that we can do serious numerical work without discussing how errors propagate. And then if we understand that enough, maybe we can understand how to minimize or limit these errors. Okay, so we want to see how errors propagate, and we want to sort of to avoid catastrophe. So we'll do a few examples in this course, and we'll show how if you're not careful about how you handle error, how you can get really catastrophically wrong results. Okay, so here's some notations that I'm going to be using. Okay, so if I use x without any decorations for the actual value, like let's say x is equal to pi, then I will use x hat for the approximate value that's being used in my calculations. So if x is the real value, say x is equal to pi, then x hat might be something like 3.14. Okay. And we'll associate two types of errors with this x. Remember, so the absolute error associated with x is x hat minus x. So the absolute value, the absolute error associated with x is the approximate x minus the actual x. Okay. Quite often, that's not so important. What's important is the relative error. This is delta x is the relative error associated with x. And that's the absolute error divided by x. So the absolute error is x hat minus x divided by the actual value x. Okay, so we would often be interested in knowing how, if we say feed a number into a function and that number has a certain error on it, how does that play into the error of the function result? Okay, so we look at the absolute error on x, the relative error on x, and then the absolute and relative errors on the result of the function that we feed this x into. Okay, so very simple example. Let's say x is equal to 10, and in my calculations, I'm using an approximate x, so I write that as x hat, and that approximation is 9.99. And then the absolute error on x is x hat minus x. and that's equal to minus 0.01. And then the relative error is given by dividing the absolute error divided by x. In this case, that would be minus 0.01 divided by 10, and that's equal to minus 0.001. Okay. Now, here's a relationship that we're going to be using in our calculations, the relationship between the absolute error and the relative error. So x hat is the wrong value. That's equal to x plus the absolute error on x. And then if you subtract out an x, so if you factor out an x, then that will give you x times 1 plus the relative error on x. So the wrong value is equal to the right value times 1 plus the relative error. Okay, so we use that a lot. And oftentimes in our calculations, we will replace the approximate value x hat by x times 1 plus delta x. Yeah. All right. So now let's see how that plays into multiplication. Okay. So I have x hat is equal to x times 1 plus delta x. I have y hat is equal to y times 1 plus delta y. Now, if I multiply these two values, how is the relative error related to the individual relative errors on x and y? Okay, so if I multiply x hat times y hat, these approximations, I will get x times y times 1 plus delta x times 1 plus delta y. And if I multiply all of that out, I will get xy times 1 plus delta x plus delta y plus higher order terms in delta x and delta y. If we're supposing that the relative errors hopefully are fairly small compared to x and y, or compared to 1, so a reasonable approximation is that if I multiply two approximations together, and I know what their errors are, and then the relative error on the result would be the sum of the individual relative errors, right? Dropping the higher order terms. We're going to do that a lot in this course. Okay, so relative errors add approximately when we multiply. Okay. Okay, so if we exponentiate, which is, repeated multiplication, then what would happen? Okay, so if we had x hat, again, the approximation is equal to the exact number x times, times 1 plus delta x. And then if we multiply that by itself 10 times, what we're going to get is the number we wanted, x to the 10, times 1 plus 10 times delta x plus something times delta x squared plus something times delta x cubed, so on up to something times delta x to the 10. Okay, so we drop the higher order terms, and the relative error given by exponentiating 10 times, given by exponentiating to the 10th power, the relative error looks like 10 times the relative error for x. Okay, so we use these kinds of this approach to work out the relative errors on various operations as a function of the original relative error on the input to the function. So exponentiating to the 10th power would give you approximately 10 times the relative error. The new relative error on the result would be approximately 10 times the relative error on the input. Okay, a result that will also come up in this course. If I take 1 plus epsilon to the minus 1, okay, there's a misprint here, just ignore that extra round bracket. Okay, 1 plus epsilon to the minus 1, provided the absolute value of epsilon is less than 1. If you recall its Taylor series, it looks like 1 minus epsilon plus high order terms, right? Epsilon squared, epsilon cubed, and so on. So a linear approximation to 1 plus epsilon to the minus 1 for small epsilon is 1 minus epsilon. Okay, so we're going to use that next. Okay, so what if we looked at relative errors when we multiply? What about relative errors when we divide? So if I take x hat divided by y hat, well, x hat was x times 1 plus the relative error on x. And y hat was y times 1 plus the relative error on y. Okay, so now I have x over y times 1 plus delta x, don't do anything with that, and 1 plus delta y is approximately equal to 1 minus delta y plus higher order terms in delta y. Okay. Now, if I multiply out the terms in the round brackets, if I multiply 1 plus delta x times 1 minus delta y plus higher order terms in delta y, I would get, the whole thing would work out as x over y, that's the value that we want, times 1 plus delta x minus delta y, and so on. Okay? So what is the approximation for the relative error here? Can anyone tell me?
Oh, 1 plus delta x minus delta y.
Okay, no. The relative, so you will have 1 plus, and then the lowest order terms are the relative error. So the relative error would be delta x minus delta y. Okay? All right. Let's take a look at addition, another common operation. So x hat is equal to x plus absolute value of absolute error on x, and y hat is y plus the absolute error on y. And so your absolute errors, when you're adding two approximations, your absolute errors will also add. Okay. What about subtraction? Okay. Well, x hat minus y hat is x plus the absolute error on x minus y minus the absolute error on y. Okay, so the absolute errors will subtract. Okay, what if I want to consider this a little bit more? We're going to look at the relative errors. So what do I want to do for relative errors? I want to divide, to get relative errors, I divide absolute errors by the quantity of interest. Okay. So you should be able to show, okay, I'll leave this as an exercise, that approximate x minus approximate y is equal to x minus y times 1 plus the error on x minus the error on y divided by x minus y. Okay? So that's the relative error on the subtraction. Okay? It's x minus y times 1 plus the absolute error on the subtraction divided by the actual desired value of the subtraction. That gives you the relative error. Now, what's the issue? The issue is that what if x and y are very close to each other? Okay. If x and y are very close to each other, then so x minus y becomes a very small number, and then dividing 1 over x minus y becomes a very large number. So the relative error can be very large if x is close to y. Okay, so this is what we this is one thing that we want to avoid. So if we know where the dangers are, maybe we can avoid them. Okay. So as such errors are called cancellation errors, and we want to be careful about those. Okay. Now, what about functions? So those were some simple operations where we considered what happens with the relative errors. Let's think about a general function f. It might be a square root, or it might be 1 plus the sine of x minus x squared, or something like that. Okay, so we have a general function, y equals f of x. So x is the input and y is the output. And I would like to know what the relative error on y is, given the relative error on x. What's going to happen? Okay, so first work out the absolute error, and then divide by the desired result. So the absolute error is y hat minus y. That's equal to f of x hat minus f of x, right? Let's assume that f calculates things out without introducing new errors of its own, okay, for the moment. So f of x hat minus f of x. And now, what are we doing? We are using this idea of linear approximation that you had from calculus 1, right? So f of x hat minus f of x, if f is differentiable at x, that's approximately equal to f prime of x times x hat minus x. Okay, so now that was the absolute error. How would I get the relative error out of this?
By dividing by the quantity of interest.
Yeah, so I would divide by y, or I would divide by f of x, right?
Yes.
Okay. So I'm going to divide by y. Okay, so that's what I've done. And now, if I want to get, I've got the absolute error, x hat minus x, right? If I want to talk about relative errors of x, then I want to divide by x. But if I want to maintain an equality, when I divide by x, I should also multiply by x. So I'm multiplying by x on the top, and I'm divided by x on the bottom. I haven't changed anything. But doing that allows me to replace x hat minus x divided by x as the relative error on x. So now I have x times f prime of x over y times the relative error on x. Okay, so what that means is I've got an x, and it's got a relative error of delta x. Now when I feed it into f, and let's say that f is differentiable at x, and f isn't introducing some numerical errors of its own, right? It's calculating everything exactly. Then the relative error on the output looks like x times f prime of x over the desired value, y or f of x. Okay? Times delta x. So that's a multiplication, right? The error on the output is this multiple of the error on the relative error on the output is this multiple of the relative error on the input. Does anyone know what this multiple is called? Okay. Yeah. All right. So if you've done a numerical analysis course before, you might have heard the word condition number. If you haven't, it doesn't matter. So this multiple is called the condition number. Okay. So the relative error on x is being multiplied by x times the derivative of f of x, of f at x, divided by f of x. Okay? So can someone tell me what happens if this, what's the significance, if I'm, supposing that I'm using repeated iterations of this f, right? Let's say I'm feeding in an x and I'm applying f to it, and then I'm applying f to it again, and then I'm applying f to it again. Then what's the significance of this multiple going to be, this condition number? Okay, all right, so supposing that this condition number is bigger than 1, and I am applying f 10 times to some input x, then it would be this condition number to the 10, and if the condition number was bigger than 1, then the relative error would be exploding, right? Okay. So problems with a large condition number are said to be ill-conditioned. All right, so let me give you an example. F of x is equal to 1 plus x squared. What's the condition number? It's x times the derivative of f of x divided by f of x. X times the derivative is twice x, divided by the f of x is 1 plus x squared. Okay, so that gives me twice x squared over 1 plus x squared. Okay, so now what if x is like 0.1? Then what's this condition number is approximately what? The condition number would be approximately 0.02, right? So there's some original error on x, relative error on x, and it gets multiplied by 0.02, right? So that gives you the approximate relative error on f of x. Well, it's not exactly 0.02, but close enough, okay? Now, what happens if x is very large? What's the condition number approximately? Let's say x is going to infinity. What is the condition number going to?
That is infinity over infinity.
Well, okay. Maybe apply. Okay, so the one, when it's, as x is going to infinity, the 1 doesn't really matter. It's approximated by twice x squared over x squared, which is 2. Right? If you use L'Hopital's rule, you could work that out. Okay, so for really, really large x, this condition number is approximately 2. Right? So now what happens if this has to be, you have a loop and you're applying this over and over again, this f, then what's happening? The initial error is going to grow without bound. Okay? Whereas you wouldn't have had, if you had some function with a condition number less than 1, then you wouldn't have this problem of the relative error blowing up. Okay. Okay. Are there any questions about this part? All right. If not, we'll move on to the next part of the lecture. Just give me a second to bring that up. I am, okay. So I hope you're seeing a slide that says floating point. Okay. So we're going to discuss now how the fact that you're representing your numbers within a computer, how that plays into this discussion that we've been having. Okay. I have to learn a little bit about floating point arithmetic, and I guess let me apologize to the CS and EE students. You know all of this already, probably. But yeah, I have to cover this so that we're sure that everybody is on the same page. Okay. So we're going to discuss how numbers are stored, what can go wrong with the storage, and again, how can we be a little less wrong? We accept the fact in all numerical work that we're wrong. Okay. How can we be a little less wrong? Okay. Once again, apologies to the CS and EE students. Okay. So how do we store things in binary? Supposing that I want to store something, I want to store a real number, and I've got 2 bits to do the storage with. So what can we store? Well, I've got the first bit, so 0. Can I store 0? Well, you're right. I can think of those 2 bits as storing a coefficient times 2 to the 0, and another coefficient that's the coefficient of 2 to the 1. Okay, so I can write 0 as 0 times 2 to the 1 plus 0 times 2 to the 0. So I can store 0. I store 1. I can store 2. What about 3? Well, I can think of 3 as 1 times 2 to the 1 plus 1 times 2 to the 0. So I can store, if I store 0, 1, I can store a 0. And if I can store 1 and 1, then I can store 3. And I can store the numbers, the integers that are in between. Okay. So, very simple example about how you would store an integer. Right? Now you say, well, no, what if I want 5? I want to store bigger numbers. Okay. So, all right, well, we'll add another bit. Okay. So if I want to add, if I say I'm going to use 3 bits for storage, so each bit can handle, can be a 0 or a 1. Okay. And the first bit represents the coefficient of 2 to the 0. The second bit, let's say, represents the coefficient of 2 to the 1. The third bit represents the coefficient of 2 to the 2. So I can store up to 7, which is 1 times 2 to the 2, plus 1 times 2 to the 1, plus 1 times 2 to the 0. Okay, so I can store up to 7. All right. Now, what if I want negative numbers? So I have 3 bits, and I can store up from 0 to 7. So what if I wanted negative numbers? What could I do? So here's one way of coming up with some negative numbers. Okay, add another bit, right? In that, so that there's a bit which is called the sign bit, and in that bit you can store a 0 to mean that the number that follows is positive, and a 1 could mean that the number that follows is negative. Okay. All right, so minus 7. So I remember 7 was 1, 1, 1, right? And I'm just going to put some symbol in between. So this leading bit is the sign bit. 1 means I have a negative. I'll put some symbol in between the bits that store the magnitude of the number and the sign bit which stores the sign of the number. So there's a sign bit which has a 1 in it, and then the other bits have 1, 1, and 1 in them. Okay, so that stores my minus 7. Okay, So now, with 3 bits, I could store from 0 to 7, add one more bit. So with 4 bits, I can store from -7 to +7. Is that okay so far?
Excuse me, sir, can you please repeat the last part?
Yeah, so before, this 7 could be stored as 1, 1, 1. I'm storing these coefficients, which are either 0 or 1 in the bits, okay, in 3 bits. So 7 was a 1, 1, 1, okay? And if I wanted to write 0, I would store 0, 0, 0. If I wanted to store 1, I would write 0, 0, 1. And then it's understood that the 0 or the 1, which is stored in these bits, is multiplying a power of 2. So if I'm multiplying by, if I'm using 3 bits, then the powers of 2 are 2 to the 0, 2 to the 1, and 2 to the 2. Okay. So now if I wanted to turn if I wanted to say that I also want to store -7, or I also want to be able to store +7, then writing 7 is can be stored as 1, 1, and 1 in the 3 bits that I have for storing the magnitude of the number. And then I can say that there's a bit that I'm calling the sign bit. And if there's a 1 in that sign bit, I'm storing a 1, and that means a negative number. What follows is a negative number. And if I'm storing a 0 in the sign bit, let's agree that I'm storing a 1 means negative in the sign bit, and a 0 in the sign bit means that what the number that follows is positive. Okay. So if I want to store -7, the sign bit, put a 1 in the sign bit, and then 7 in the other bits is 1, 1, 1. And that means 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2. Okay. Now, what if I want even bigger numbers? Then you might say, well, you had 3 bits before. What about trying for 4 bits? I can then sign for bigger numbers, right? But then you'd say, well, no, I want to get some really big numbers, right? So then you might say, let's do it this way. We're going to have 1 bit for the sign. We're going to have 3 bits for the exponent. And we're going to have, say, 4 bits for a number. Okay? So let's see how we would. So this is an 8-bit arrangement. So this is how we would store the numbers. So in the 4 bits, which are for storing the number before any exponent or the sign, we can store up to 2 to the 0 plus 2 to the -1 plus 2 to the -2 plus 2 to the -3. Okay? So that it's understood that in the 4 bits that are for the number, those bits are the coefficients for 2 to the 0, 2 to the -1, 2 to the -2, and 2 to the -3. Now, I've got 3 bits for an exponent. So the 3 bits for the exponent, I can store up to 7. Right? The exponent could be 2 to the 0. Right? You know, my number could be multiplied by 2 to the 0, 2 to the 1, 2 to the 2, and up to 3 bits. The most that I can store with 3 bits is 7. So I can multiply by the number by up to 2 to the 7. Multiply by 2 to the 0, 2 to the 1, 2 to the 2, up to 2 to the 7. And I've got 1 bit for the sign, so that could be 0 means a positive number follows, or 1 could mean a negative number follows. So I can store a number like minus 240 the way it's written out here.
Sir, I'm not able to understand this thing. Like, why did you take negatives in the power of 2 before? Earlier, we were taking positive only 0, 1, 2.
Yeah, okay. So what I'm going to do is, okay, so 2 to the 0 is 1. So imagine that I'm taking, remember when we use, say, exponentiation using powers of 10? We write something like 2.36 times 10 to the 7, right?
Yeah.
Right. So the 0.36 is being written with negative powers of 10, right?
Yeah.
Right. So that's what this factor on the right-hand side is. We're going to take numbers that look like 1 point something, and then we're going to multiply them by an exponent, and we're going to multiply them by a plus sign or a minus sign.
Oh, okay.
Yeah. Okay, so we can get minus 240 if we flip the sign bit from a 1 to a 0, we could get plus 240. Okay. Okay, so now this number, minus 240, if I want to think about how it's working in the computer, all I want are the coefficients of the various things, because the place in the number tells me what tells me about various things. So 2 to the 0 plus 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3. These powers of 2 are all being multiplied by 1s. So here, for the number part, I just need to put in 4 1s. Okay? And let's agree then that the middle part is the exponent. So in binary, how do I write a 7? I write 1, 1, 1. So this is understood to stand for 2 to the 7. This middle piece in here stands for the exponent. So this is the exponent, 2 to the 7, which is multiplying this 1, 1, 1, 1 in binary. And then I wanted a minus sign. So I'm writing a bit. The sign bit gets a 1. So the first bit is the sign bit. Then there are 3 bits, which are the exponent. And then there are 4 bits, which stand for the number. Okay. All right, is that okay? Right, so this number is 1 times 2 to the 0 plus 1 times 2 to the minus 1 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 3 multiplied by an exponent of 2 to the 7 multiplied by a sign of minus 1. Okay, and this thing, this representation here is a way of representing how it's actually stored in a computer. Is that okay?
Yes, sir.
All right. Now, what if I want negative exponents? Okay. I don't want to multiply by 2 to the 7. What if I want to multiply all of this by 2 to the minus 3? Okay. So here's one way to get negative exponents. And what we do is we say that whatever exponent this looks like, okay, so this looks like an exponent of 7. What I want you to do is I want you to subtract off something. We call that the bias. So let's make that a bias of 3. Okay? So if we go back to here, here's some number, and then there's an exponent of 2 to the 7, but now I'm saying there's a bias of 3. That means whatever it looks like in binary, I want you to subtract 3 off of that. That's what I actually mean. So if I write this to mean 2 to the 7, there's an exponent of 7, and then I say the bias is 3, then 1, 1, 1 doesn't mean 7 anymore. It actually means 4. Okay? What if I wrote 0, 0, 0 here in the exponent? What would that mean?
2 to the power 0.
Right, but so it's no longer 0. You've got instead you've got a
One.
bias of 3. So what do you have? Instead of 2 to the 0, you have 2 to the,
-3.
right, you have 2 to the -3. Okay, so now I can no longer multiply by -7, by 2 to the 7, right? Before, without any bias, I could multiply by numbers from 2 to the 0, 2 to the 1, 2 to the 2, up to 2 to the 7. Now with a bias of 3, what are the numbers that I can multiply by? This middle part says I'm multiplying by some number. What are those numbers that I can multiply by? Well, the smallest number that I can write in binary here is 0. And with a bias of 3, that means that I can have an exponent of -3. And the largest number that I can write with 3 bits is 7. So that means I'm multiplying by 2 to the 7, but there's a bias of 3. So I'm multiplying by 2 to the 4. So if I have a bias of 3, what that means is whatever number I've got on the right, I can multiply it by 2 to the -3, 2 to the -2, up to 2 to the 4. Okay, so if I have a bias of 3, I can no longer multiply by 2 to the 7, but I can multiply by up to 2 to the 4. And I've still got a sign bit. Okay. Okay. So once again, if I wanted to write 6, in binary, I would write that as 1, 1, 0, but 6 now means 3 if I use a bias of 3. If I want to write 0, 0 in binary using 3 bits is 0, 0, 0. With a bias of 3, that actually means -3. Okay, so here's an example. Minus 0.25, if I think in terms of powers of 2, well, there's a minus sign, times 2 to the -2 times 1 plus 1/2. So now how do we store this? The -1 is stored as a 1 in the sign bit. Now what's the exponent? It's 2 to the -2. Okay. Well, -2 plus 3 is 1. So in binary now we want to write 1. Well, with 3 bits, that's 0, 0, 1. And now what's the number part? That's 1 times 2 to the 0 plus 1 times 2 to the -1. And then I don't need anything else, so the rest are zeros. Okay, so using 8 bits, this is how I can write -0.25 and store it in a computer. Is that okay?
Yes.
All right. But that was with 8 bits, right? And how do we actually store the real numbers? Actually, we can't even really store all of the reals. If you think about this a bit, you'll realize we can only store rational numbers. And we can't even really store all the rational numbers. But anyways, if you want to use 32 bits, all right, so the IEEE has defined this way, using 32 bits. So the sign is negative. The number part is 1.234, right? We call this the mantissa. And then the exponent is 12. Okay, so that's the real number in our usual base 10 notation, right? The sign is negative. The mantissa is 1.234, and it's being multiplied by 10 to some exponent, and the exponent is 12. Okay. Now what we do is we take the fractional part of the mantissa. Okay, we had 1.234, take out the 1, because storing a 1 is easy, so we don't need to worry about that really. So this is a 0.234. Now let's expand that out. That's 2 times 10 to the minus 1 plus 3 times 10 to the minus 2 plus 4 times 10 to the minus 3. All right? All right. So now let's think in binary. Supposing that I've got plus 1.000, okay, positive 1.011 times 2 to the 5. The sign is positive. The mantissa is 1.011, and you're multiplying by an exponent by 2 to the 5, so the exponent is 5. Okay, is that okay? All right. Now, how do we write out that mantissa? Right? 1 times 2 to the 0 plus 0 times 2 to the minus 1 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 3. Okay. Now, how do we store it? Well, we say that there's a sign bit. Because it's a positive number, we store 0 in the sign bit. Now, there's an exponent. Okay. What was the exponent? The exponent was 5. Okay. So we allow up to 8 bits for the exponent. And then we have a mantissa, and we allow 32 bits for the mantissa. Okay. So that's in general how an IEEE short real number is stored. Okay. So 1 bit for the sign, 8 bits for the exponent, and 23 bits for the mantissa. So that's up to 32 bits. We also use the phrase single precision for this format. Okay. Now, if you wanted to store bigger numbers, there's another format called the IEEE long real. So 1 bit for the sign, 11 bits for the exponent, 52 bits for the mantissa. I don't really expect you to remember all of these things, but you should have an idea at least of how things are being stored. Okay, that uses 64 bits for everything. And we frequently use the phrase double precision for this. Okay. Now, okay, how are we going to store the sign? As before, 0 means plus, means that the following number is positive. 1 means that the following number is negative. How do we store the mantissa? Well, 23 bits. The most significant bit is to the left. Okay. The exponent doesn't have a sign, right? The way we get negative numbers is to give a bias. So we have 8 unsigned bits, and we have a bias of 127. Okay. So if the exponent is 6, we store 133, right? The binary for 133 is this string down here. And then we subtract 127 from it, we would get 6. So this is how you would store an exponent of 6. Okay. If the exponent is -2, and there's a bias of 127, add 2 to that, you'd get 125. And then when you have 125, well, storing 125 in binary is done this way. Okay, now we're going to do a little bit with the mantissa. Supposing that the number I'm dealing with is 101.001, then what I'm going to do is I'm going to, this is in binary, right? I'm going to move the decimal place over to the left by 2, and then I'm going to multiply by 2 to the 2. Okay, so this is the way I want to be thinking about that mantissa. Okay, and so if you're going to do that with every number, you're going to normalize the mantissa in this form. So that means that with every single number that you're going to try and store, there's always going to be a 1 point something. In binary, you will always have this 1.1 or 1.0 and some ones and zeros afterwards. So that 1 is always going to be there. And if 1 is always going to be there, then we can just understand that the 1 is there, and we don't have to store it. Okay? We don't need to store it anymore. So if I want to store -1.11 in binary, okay, so the minus is a sign, that's in the sign bit, put a 1, okay? Now, the biased exponent, we're not, this 1.11 is not being multiplied by 2 to the 0. So the way to store 0 is actually bias of 127 is to store 127. So then we write 127 in binary. Now I want to store the mantissa, but the mantissa has a redundant 1. So I really need to store 0.11. So then I just store 1, and then all of the rest are zeros. Okay, so that's how I go about storing things in this IEEE form. Okay, why am I doing all of that? The reason I'm doing all of that is to show you how that's done, and then if we're dealing with more than one number, and we're doing some operations, what are the issues that arise? Okay. So with IEEE short real, what's the largest magnitude of number that can be stored? Or for IEEE long, what you should think about, what's the largest number that can be stored? Okay. Or I suppose you could always look those up. Now, after that long discussion, what does this have to do with let's see how that plays into the arithmetic. Okay. All right. So this is what it's looking like. Our numbers, what is it that we're actually storing? So we've got -1 to a sign bit. So we're storing this sign bit S. Then we've got ×2 to an exponent, and we're storing that exponent E. And then we've got times a normalized mantissa, which always has a 1 in front of it. So it's 1 point, B1, B2 up to BP, right? And I don't need to store the 1 because that's always understood to be there. So I need to store the B1, B2 up to BP. Okay, so I'm storing this S, I'm storing this E, and I'm storing this B1, B2 up to BP. Okay, remember S is between 0 and 1. Yeah, there's a question, Eswanya?
Yes, sir. If you always assume 1, then how do we store 0? Because
Oh.
Yeah.
How do we store 0? Okay, does anyone else, can anyone else tell me? Okay. Is this something that I've left out of the discussion, maybe, you think?
So if the exponent part would be 0, so, if it is 0, then the whole exponent part would be 0. Is it?
Oh, if the exponent is 0, then that's 2 to the 0, which is 1, right?
As far as I understand the question, he is asking that we always store the part 1, but instead, if there is a 0 instead of 1, then how we store that 0? Is it?
Yeah,
Is that a question?
how do I represent a 0?
So I'm saying that if that part would be 0, then the whole exponent term would be 0. Is it?
No, well, I mean, we've got 0 times 2 to the 0. So that would be 0 times 1.
No,
Which
the
would
2
still be
times
0.
whatsoever the value, whatsoever the power is, the whole part is multiplied with the 0, and then it becomes 0.
All right. Okay. I don't want to give this away too quickly. Okay. Okay. So let's say that that's an interesting question, and let me take my prerogative and not answer it right away. Okay.
Okay, so that's fine.
Okay. So so B1, B2 up to BP, and P is your 52nd bit. Okay. Okay. So that's what we need to store. Oh, that looks like a repeat. Okay. So you will realize then that we cannot even store all the rational numbers. Okay. So we're going to talk about rounded representations then. So if I have a real x, and let's say FL of x means the closest floating point number to x. Out of all the floating point numbers that I have available to me, using whichever standard I've decided, let's say it's the 64-bit double precision standard, whichever one I have, this FL of x means that's the closest floating point number, the closest thing that I can represent in my machine to that x. Okay. So what if I have, what if there are two such numbers, right? One might be a little bit bigger, but one might be a little bit smaller, and they're both equally close. Then one of them will have a 0 in the last bit, and the standard is to choose the number with a 0 in the last bit. Okay. Well, then naturally this leads to a question. If x exceeds the maximum floating point number, what happens? There's some maximum floating point, largest floating point number that my machine can handle. And without resorting to software solutions or something like that, what happens? Well, my FL of x, I call that result infinity, which is painful to mathematicians to use infinity in this way, but okay. Okay, so how do we represent infinity? Infinity, any overflow, we have to have some way of representing it, right? So this is the way that we represent it. I guess we say it's, right? 0 for the sign bit, all ones for the exponential part, all ones for the exponent part, and all zeros in the in the Mantissa part of the representation. Okay, machine epsilon. Okay, so this is the magnitude of the smallest number that I can manage. So that would be if you put all zeros in the exponent part, right? And then you've got all these bits for the Mantissa, and you have all zeros except for the last one, the least significant one. Then the number that you're going to get is 2 to the minus 53, which is about 1.1 times 10 to the minus 16 in our, well, in human terms. So the smallest non-zero magnitude number that you can represent is 2 to the minus 53. Okay, so as an example of something that can't be represented exactly, 0.1 can't be represented exactly in 53 bits. 0.1 meaning in decimal terms, in base 10. It can't be represented exactly in 53 bits. Now, 0.2 in base 10 can't be represented exactly in 53 bits. So if we put them together, we add them together, then they're going to come out as, well, you're going to have this little bit of error showing up, right? Okay. So, yeah. I'm not going to force you to memorize all the details of that. The big takeaways are this, that there is a way to represent a range of numbers, not all numbers, and in using binary bits, storing zeros and ones. And these will not allow us to certainly to represent all the irrationals, and even the rationals, 0.1, 0.2. Not even all rationals can be represented, and so we should expect that there should be some round-offs. Okay. And from the previous thing, the big things were this idea of absolute error. Typically, what's really important is the relative error. And then if we're dealing with functions, then the important thing is what is the condition number of a function. Okay, so I hope that's okay. Are there any questions before we log off? Okay, if there are no more, yeah.
Sir, I wanted to ask if the recordings will be uploaded on YouTube or LMS. Or what?
Yeah, I will. I'll put my recordings up on YouTube and send you the link. Okay.
All right, that would be great. Thank you so much.
Okay then. Well, that's. I will see you then on Friday.